Hello and welcome to the course on Geotechnical Engineering. In this first module, we'll be laying the foundation, pun intended, for your understanding of how soil behaves under different engineering conditions. Our focus will be on the following key areas: stresses in soils, consolidation and settlement, shear strength of soils, earth pressures. Let's begin with understanding the basic stresses in soils. Headphone 1. Stresses in soils. Soils are not just passive materials beneath our feet. They respond to every structure and load we apply. Stress in soils refers to the force distributed over an area. In geotechnical terms, there are three main types. Total stress. This is the full pressure acting on a soil mass. Pore water pressure. This is the pressure within the water held in the soil pores. Affective stress. This is the portion of the total stress that is carried by the soil skeleton and is what actually affects strength and stability. Understanding affective stress is crucial because it's the actual stress that influences settlement, stability, and failure. When a load is applied to the ground, such as from a building or a bridge, that stress is transmitted through the soil layers. The further you go into the ground, the more distributed this stress becomes. Engineers use several methods to estimate how deeply a stress will reach and how much it affects the soil at various depths. Headphone 2. Consolidation and settlement. Settlement refers to the gradual sinking of a structure as the soil underneath compresses. This process is most prominent in clay soils and occurs in stages. Immediate settlement happens right after a load is applied and is typical in sandy soils. Primary consolidation is the time-dependent compression of saturated clay as water is squeezed out of its pores. Secondary settlement is the slow adjustment of soil particles that continues even after water has drained. Terzaghi's theory of one-dimensional consolidation is widely used to model and predict how long and how much a clay layer will compress under a load. Engineers use laboratory tests like the oedometer test to evaluate how compressible a soil is and to estimate how much settlement will occur over time. If settlement is not properly accounted for, it can cause structural damage, especially if the settlement is uneven. Headphone 3. Shear strength of soils. Shear strength is the soil's resistance to sliding or shearing. It determines how well the soil can hold up structures, support slopes, and prevent failures. Soils derive their shear strength from two main components. Cohesion, which is the internal stickiness or bonding of particles. Friction, which is the resistance between particles as they slide past one another. Cohesive soils like clay tend to have both cohesion and friction. Sandy soils, which are cohesionless, rely primarily on friction. To assess shear strength, geotechnical engineers perform several tests. Direct shear test measures resistance along a known plane. Triaxial test, more sophisticated and simulates different loading conditions. Vane shear test, used especially for soft clays in the field. These tests are performed under drained or undrained conditions. Drained conditions allow water to escape, while undrained conditions occur when water cannot drain, which is typical during rapid loading. Understanding shear strength is vital for safe design. A slope that looks stable might fail during a rainstorm if pore water pressures rise, reducing the soil's ability to resist shearing. Headphone 4. Earth pressures. Soils can exert lateral forces on structures, such as retaining walls, basement walls, or bridge abutments. This force is known as earth pressure, and it changes depending on how the structure moves and the type of soil. There are three types of earth pressure. At rest pressure, when the wall does not move. Active pressure, when the wall moves away from the soil, causing the soil to expand. Passive pressure, when the wall pushes into the soil, compressing it. The magnitude of these pressures depends on soil type, wall movement, and depth. Engineers use theories such as those by Rankine and Coulomb to estimate earth pressures. These theories provide practical tools for calculating how much pressure a wall must resist, depending on whether the wall is fixed, moving slightly, or being pushed into the ground. Understanding earth pressure is essential for designing safe retaining structures. A miscalculation could mean either a wall that is too weak and fails, or one that is unnecessarily expensive and over-designed. Headphone conclusion of Module 1. That's the end of Module 1. Here's a brief recap. Stresses in soils include total, pore, and affective stress, with affective stress being the most critical for design. Consolidation and settlement are time-dependent processes, especially in clays, and must be evaluated to avoid structural damage. Shear strength is a fundamental soil property and is the key to resisting landslides and structural failures. Earth pressures influence how walls and buried structures are designed.